All right, friends, welcome back. In this video, we're going to take a look at section 3.5, and take a first day for this one. And we're going to switch gears a little bit. So where we have been in chapter 3 already is we've been talking a lot about polynomials in general, how to do various things with them. But in this video, what I want to do is I want to focus more on the idea that an equation represents a relationship, okay? And we're going to talk about a couple of specific types of relationships as we go through the video here. But yeah, let's get started with that. So first and foremost, one of the things that you may recognize is that sometimes when we look at equations, they have the variables in that equation have more of a direct relationship, okay? And so as an example of this, maybe you take a look at your after-school job, right? So when you get paid, what happens is the amount of money that you get paid, like maybe say Y, that is directly related to the number of hours that you work. And that relationship goes, you know, the more hours you work, as the hours you work increases, your pay increases because you get paid for each of those hours, right? And so this is what we call a direct variation because of the definition up here, right? It says as one amount increases, the other amount increases at the same rate. So I really like that example of, you know, the number of dollars as it relates to the number of hours you work. The more hours you work, the more you get paid. So they grow together, okay? And so what that means here is that there is some sort of constant right here that we would multiply times our number of hours to calculate the number of dollars we're going to get paid, okay? And so if you think about that really quickly, what that means is that is basically just going to be your hourly rate, okay? That is going to be how many dollars you get paid per hour, and in general, that is how we might interpret that value of K there. That is something that we call the rate, or something that stays constant, so we call that the constant of proportionality. And that's similar to slope, again, because what we just said is that represents an actual rate, okay? And that's how these quantities are related, all right? Now, as we go through and take a look at some examples, you may notice that in order for you to recognize that you have this sort of relationship, they're going to actually use that language. They're going to say that one variable relates directly or varies directly as the other one, okay? So that's a quick example of that. Another type of example might be this other type of relationship where maybe instead of two quantities growing together, you maybe have one quantity growing while the other one decreases, right? So if you're anything like me, you have a million different apps and photos and various things taking up storage space on your phone, okay? And so what you might say is a way that you could calculate your storage on your phone is to take a look at the number of things that you're downloading to your phone. The more things you download to your phone, the smaller and smaller and smaller your storage is going to become. So I'll just say here simply number of apps, whatever, okay? And so this is something that's different from a direct relationship where both of my unknowns are growing together. What we have here is as one quantity grows, the number of things on my phone, the other quantity gets smaller and smaller, so the amount of storage space on my phone, okay? And so that's an inverse variation. As one value decreases, the other increases, okay? So as a tip to let you know that we are dealing with this sort of thing, we are going to take a look at the language that they use. Again, they're going to say varies inversely. And for all practical purposes, instead of using this division symbol right here, you're going to find that it's going to be more useful for our purposes if we go ahead and get into the habit of writing it as a fraction just like this, okay? And so what I would like to do is go ahead and take a look at a couple of examples where we are looking at how to model equations in this light with these two different relationships here. And before we move on to that, what I want to do is I want to come back up to direct variation real quick and let you know about a special situation, right? Because sometimes in an equation, you might be relating three things instead of relating two things, okay? And so an example of that might be like simple interest, right? Your interest depends not only on time, but it also depends on the principal amount that you first put into an account, okay? And so interest depends on two things, time and your principal. And so that sort of thing is called joint variation. I want you to write that down because this will come up for us. Joint variation, and the model for that, since we have three different unknowns, is we're going to introduce the variable z, okay? So just following the alphabet, z is equal to that constant of proportionality times the product of x and y, okay? Where we're saying here that z depends on both x and y together, all right? And so whenever we're doing these types of problems, I'm going to go ahead and skip what we have here in example 1. You can see here that what these examples require is that we basically just kind of go through and determine if the model demonstrated is direct or inverse or neither. Truth be told, that is going to be less of a focus of ours, and more of a focus of ours is going to be actually writing down the model and using the model. So I'm going to skip to example 2 here in the notes, where it says in the directions, write a mathematical model that represents the statement. And you notice that I've already gone through and done a little bit of highlighting here, because again, in each one of these examples, they're going to tell you what kind of variation you're going to be working with between your two unknowns, okay? So I just want to go through some of these examples and just kind of demonstrate how we would go ahead and write the model for each one. So part A, it says the simple interest for a certain savings account is jointly proportional, if OneNote bothers to load that, there we go, is jointly proportional to the time and also to the principal. This is the example that I pointed out a few moments ago, okay? Now, you'll notice that they don't really give us any sort of variable names for these, so you could pick whichever ones you want, but in general, it's a good idea to pick some variable names that if you were to look at it, you say to yourself, oh yeah, that represents interest, or oh yeah, that represents time, okay? So for that matter, let's go ahead and see here that simple interest, I might just go ahead and let that be represented by a capital letter I for interest. Again, so if I look at that, I remember, oh yeah, that's I for interest. Same thing over here on time. I might say T for time. And for the principal amount, that's your initial starting amount, I might just go ahead and call that capital P. That's what you'll typically find. Most textbooks would let that represent, okay? And so now we come over here to where it says jointly proportional, and we start to write our model, right? So what it said is that simple interest, which we called capital I, is jointly proportional. So what that means is that I is equal to some constant multiple of your time and your principal, okay? And so it's going to be equal to some sort of constant of proportionality times your principal times time, okay? And I'm not trying to trick you. As far as writing the model down is concerned, that is absolutely what we need, okay? So it's just a matter of figuring out what kind of variation you're dealing with, either direct, inverse, or joint, and then using those models to write your model down for that situation. An interesting example here in part B, we'll see this as a common trend in future examples here too, is that we basically have two different kinds of variation. And so I want to kind of take this one little bit at a time, right? So we start off with, in part B, we have this quantity capital F, and then it's going to say here that it varies directly as G. Okay. Separately, they're going to say that F also varies inversely as R squared. Okay. So separately, I want to kind of think about what these would look like, and then maybe put them together in a combined model, right? So if F varies directly as G, we know what that looks like. That would be capital F is going to be equal to some constant multiple of G. So that would be what that model would maybe look like. That is with K being multiplied times something if it's directly. And then for inversely, we know that capital F would be related to that other quantity by a K divided by, okay? And so you notice that it's inversely related to R squared, and so to write that in symbols, we would simply just use our exponents and just say R squared, okay? And so if I have to do both of these at the same time, you notice that word and in between, I have to account for that first model and at the same time that second model. What I might do is notice that both of these models require that I talk about this constant multiple K, okay? And so when I combine these two together, I'm going to basically go ahead and say here that F equals K times G, because of the direct variation, and then divide this whole thing by R squared. That will account for the K divided by R squared that I said I should have from over there. Okay, so combining two models together in that way is going to be something that we are going to pretty commonly do when we go from example to example here. So part C here, pretty quickly, again, it just says varies inversely as Y, and then varies directly as Z. So to write the model down for that, we would say that X is going to be related to Y by an inverse relationship, so K divided by Y. Oops. And then it varies directly as Z. So up here, I'm just going to go ahead and say Z times K to account for that direct variation there. Okay? And so there's your model. Very good. All right? In that next one down, it says Y varies jointly with Z and the square root of X. Okay? What you're going to find is that they're typically going to describe something verbally to you, and we just want to translate that to symbols. We know what the square root of X looks like. It would just simply look like that, radical X. Okay? And so here, if we're varying jointly, that's going to be a direct variation, right? So that's going to be Y is equal to some sort of constant multiple of z and the square root of x. Very simply done. So joint variation is basically identical to direct variation, except you're relating 3 unknowns instead of just relating 2 unknowns. Part E, it says w varies inversely with the cube of x. So real quick, the cube of x, what are they talking about there? Well, that's just x cubed, or in other words, x to the power of 3, okay? So w varies inversely as the cube of x. Let's write that down, right? We know what that looks like. That's going to be your k divided by, and so that's going to be k divided by the cube of x, or x cubed, and then jointly with y squared and z. So if that's jointly, keep in mind that's a direct variation, and so that's going to be k times y squared and times z there. Okay, so as far as our model is concerned, this is exactly what we would want it to look like right here. That accounts for both types of variations we were told. Okay, so part F, it says y varies jointly with the square root of the product. Okay, so that's some different language that they're using there. So first of all, the square root, we know what that looks like. That's just a radical. Oops, think the shape. There we go. And now what they say is this. It says the square root of what? Well, the square root of a product, okay? And so this is one of those words from earlier math classes from elementary and middle school where you relate this word to a certain operation in mathematics. And when they say the product, of course, what they mean to say there is that you are multiplying, okay? So we want to take the square root of multiplying x and z. And so, of course, what that would look like here is going to be this. I'm going to have the square root of x times z, okay? So if y varies jointly with this, then what we're going to go ahead and say here is start that off by saying our model looks like y is equal to some sort of constant multiple of the square root of x, z. Okay, relating those 3 unknowns there. But we're not finished, because then it continues to say that y also varies inversely with w. And so to finish off our model, I might just go ahead and say here divided by w, and that would complete the model. Okay, so y is equal to k times the square root of x times z, all divided by w. All right? As the last example of this little set of examples here, we start off very simply. Z is going to vary directly with x, and so we can start that off. We know that that's the k times relationship, so some sort of constant multiple times x. And then we'll pick up here, and it says is inversely with the cube root of y. So the cube root of y, we know what that looks like. That's a cube root, so that's a radical symbol with an index of 3. So the cube root of y would look like that in symbols, and then, of course, z squared, okay? So if we are inversely with these two quantities, then that means that, of course, we're going to be dividing our constant of proportionality by those two quantities. And so I'll say here the cube root of y, and then times z squared. You'll notice that I'm not putting the z squared under the cube root, because if they wanted me to do that, they would have said something very similar to what they did in the last problem, where they say that we want to do the square root of the product of 2 unknowns. But here they didn't do that. Here they just said the cube root of y and only y, and then separately z squared. And so that would complete our model for that problem there as well. Okay, not too shabby. So whenever we read through the language of the problem, we very closely have to pay attention to whether they say directly, inversely, or jointly, and then we have to pay very close attention to just various different things that we can write with symbols, like square and cube roots and exponents of 2, exponents of 3. Also paying attention to like part F, where they say the product of 2 things. Again, just being able to make sure to read those very carefully so that you can translate them correctly is something that's very important, okay? So in part 3 here, you'll notice that I've already done some highlighting ahead of time just so we can kind of point out what types of variations these are. And the only thing that makes these problems different is that we are now going to take the model that we come up with and plug some values in, because you'll notice that in these examples, I'm basically giving you some values to plug in as you go from variable to variable, okay? And so I want to kind of take a look at that here, right? So in part H, it says f varies jointly to r and the third power of s, okay? So varies jointly means that we're going to be related to these 2 quantities here. The third power of s, of course, is just s to the third power. And so we could write that model in a little bit of a way that looks like this. F is going to be jointly proportional, which means that it's some sort of constant times your 2 other unknowns, so r and s cubed. Okay, and now in gray they're highlighted, they gave us some values to plug in for f and r and s, and we just have to plug those in, because you'll notice what they ask us to do is they ask us to find what k is and then write out an equation of proportionality. We'll talk about what that means here in a moment. But what we're now going to do is we're just going to go ahead and plug in the different things that we know can be substituted in for these variables, right? So f, we were told, is equal to 4,150, was it 8? Yes, 4,158. We're just going to plug that in, and we're going to say that that is equal to k times your r value, which was given to be 11, and then times your s value, which was given to be 3, okay? And so we'll say that that is 3 cubed according to our model, because remember, it was the third power of s, all right? And so now we just have an equation here, and we're just going to go ahead and use our algebra skills to solve the rest of this equation, all right? You notice that right here on the right-hand side, I've got 11 times 3 cubed, and so you can go ahead and bust out a calculator to perform that calculation really easily. If you were to do that, then it would give you 297. So on the right-hand side, that turns into 297k, and then on the left-hand side, we still have that 4,158, and then to solve the rest of the equation, what we simply might just want to go ahead and do is divide both sides by that 297, in which case you would get the following result, right? We would have these guys canceling for us, 297 over 297, and so that leaves us with k by itself on the right-hand side, and then we're just going to go ahead and perform 4,158 divided by 297, and that is going to give us 14. Okay, and so that is our constant of proportionality. We actually have a value for that now, and the reason that we do is because they gave us those values for all of the other unknowns in our model. Okay, and now what they ask us to do is to go ahead and write ourselves an equation of proportionality, and all that is writing our initial model, but with k plugged in now that we know what it is. Okay, and so our model did read f is equal to k times r times s to the third, and now that we know what k is, we're just going to go ahead and substitute that in for our k, and then there is our equation of proportionality right there. Okay, so f is equal to 14 times r times s cubed. All right, so I'm actually going to go ahead and skip I for the sake of the video here, part I. It would be the exact same problem as part H, just setting up the model, plugging in some values, and then figuring out what your equation is going to be equal to. Again, check the content library later for the more complete version of today's notes here. But the last one that I'm going to do in the video is going to be part J, where it's an actual application problem. So let's take a look. So it says in part J, the number of songs that can be stored on an MP3 player varies inversely with the average size X of a song. So weirdly enough, they gave us a variable term for what the average size of a song was, but they didn't give us a variable for the other thing, which is the number of songs. And so what we may want to do here is just give that a really quick variable name. Maybe just keep it simple and call that Y, since we've already used X for something else. And then keep in mind here that we are varying inversely, and so our model would simply look like this. Y is equal to some constant divided by X. Okay, and then in that next sentence there, they give us some background info. And so they say here that a certain MP3 player can store 2,500 songs when the average size of a song is 4 megabytes. Okay, well, keep in mind the number of songs, that is what we called Y, and the average size of the of your song is going to be X, right? And so if we just simply go ahead and substitute those values in place of Y, I'll put 2,500. In place of X, I'll put 4. We are just going to go ahead and now solve this equation for what that constant of proportionality is, and of course that's k, right? And so we could solve this really easily by just simply multiplying both sides by 4, and we are going to get a pretty large value for k here, but that's completely fine. We're going to get 10,000. All right, and then what they did there is they asked us to write the equation of variation for this situation. Equation of variation is the exact same thing as equation of proportionality from part H. So they just want us to go ahead and rewrite the model with our constant of proportionality plugged in here. So that is going to look like Y is equal to 10,000 divided by X, and that completes the problem. Okay, so that is the model of variation for how the number of songs in this MP3 player relates to the average size of a song. Okay, and so that is going to do it for this video. Again, just kind of taking a look at a couple of different scenarios where we have direct, inverse, and joint variation, and writing the models down for each one. So make sure you're clear on the difference. If you guys have any questions whatsoever, as always, feel free to let me know. But that's going to do it for this one. Thank you very much for your attention, and I'll speak to you in the next one.